All right, so last time we looked at how to solve linear second order homogeneous differential equations. And we saw that there was a great pattern. And so Trey just put in that he had some questions on the homework. So let's go look at those first. So from 5.1, he'd like to look at numbers 9 and 14. So I'm going to go ahead and share my screen. We'll go look at those. Okay, so you should see my screen here pretty soon. He says waiting, hopefully. All right, there you go. Okay, so let's go look at that. Okay, so the stuff from 5.1, it's not actually the find the solutions. It's more talking about the theory, in terms of where we have solutions and all that. But let's look at number 9 here. So number 9 says, it shows that if you know one of the solutions to the differential equation, you can actually use Abel's formula to find the other. Okay, so let's see what it says. So we have P and Q are continuous, and Y1 is a solution to this homogeneous second order. All right, so the fact that P and Q are continuous means that we know we have a unique solution for any initial value problem, right? And then it says that it has no zeros on A to B, so that's an interval where we know it's going to work. So then let P of X, big P, be the integral of little p. So show that if K is an arbitrary non-zero constant and Y2 satisfies this thing, then Y2 satisfies the original differential equation, and Y1 and Y2 form a fundamental set. All right, well, let me write this up on the board so that we can do some work here. But let me get the important information. Okay, so let me go to the board. I'm going to stop my share here. We'll come back for part B or whatever in a second. All right. So here's what we know. We've got this differential equation, the y double prime plus p of x y prime plus q of x equals y, or y equals 0. And then we're told that y2 satisfies the second one. So real quick, I just want to confirm. Can you guys hear me? Yeah, thumbs up. Okay. Because I actually can't hear me in my earpiece, which is a little weird. So I don't know what's going on there. All right. So what we want to do is actually show that then this y2 is also a solution to this differential equation. So in essence, like this is really where we're going, is that if you know y1, you can find y2 by dealing with this, by using this step right here. And then the hope is that once we have y2, we know that it's it goes with y1 to form a fundamental set. Okay, so how do we show then that y2 actually satisfies this differential equation? You guys have any ideas? How about this? If I were to give you a function Just say, hey, y2 equals blah. How would you confirm that it's a solution to this differential equation? Okay, so Trey just said plug it in, right? And he actually said solve for y2. Yeah, how about we solve this thing for y2 or y2 prime and all that, and actually plug it into the differential equation and see what happens. So here's what I'm going to do. Let's take this first one, this relationship, because we were told, hey, if this, show that y2 is a solution. I'm going to start by solving that for y2 prime. So I'm going to move the y1 prime y2 over here. And then if I solve that for y2 prime, this is where we are. So again, I don't know anything about y2, but I do know that its derivative is going to equal this. So when we go to try to figure out what happens with y2 and see if it's a solution, right, we're going to want to plug y2 in for these pieces. I've got something that I can now plug in for y prime. y2 prime is going to equal this. Of course, y is going to equal y2. But I do need one more piece. I actually need y2 double prime. So to get y2 double prime, let's differentiate this with respect to x. So this is going to require all sorts of nasty quotient rule stuff, and also a little product rule as we go. But let's do it as maybe, we'll do it individually with the different quotient rules. So for the first one, I need a derivative of the top times the bottom. So the derivative of the top is going to be k times e to the minus px times the derivative of the minus px, which is going to be negative little p of x. So that's the chain rule on this. Ke to the minus px times little minus px. Because little p, it was a thing that when we integrated gave us big P. And then I need to multiply by the bottom, so y prime, or y1, I mean, minus the derivative of the bottom, y1 prime times ke to the minus p of x, all divided by the bottom squared. Okay, so that is the derivative of the first piece. Okay, so then I need a derivative of the second piece. So I know I've got my line drawn here, but I can see from the screen, you can see a little bit lower. So I think, let's see, where are we? Oh, yeah. Okay, I think I got that much space. All right, so then we need to add to that the derivative of this piece. So this has product rule and quotient rule. So the derivative of the top is going to be y1 double prime y2 plus y1 prime y2 prime divided by the bottom squared, so y1 squared. So that's the derivative of the top times the bottom, which is y1, minus the derivative of the bottom, y1 prime, times the top, y1 prime y2. And then that's all divided by the bottom squared. So I think I barely fit that onto your screen. But that's the quotient rule from that thing.
What's the second part of that numerator?
So I'm sorry, Trey, say that again.
The second part of the numerator after the minus sign. What is that?
y1 prime minus, or sorry, y1 prime times y1 prime y2,
Okay.
not y squared.
Thanks.
Yeah, you're welcome. Thanks for catching my mistake. All right. Well, now we get to plug that back into the differential equation with also the y prime. And let's see what we get. So we're going to get y double prime. So that's all of this. Let me simplify it a little bit because we can definitely do some things to it to make it look not so gnarly. We're going to get k e to the minus p of x times a minus little p of x. I'm going to go ahead and cancel the y1s on that. So this is just over y1. And then minus y1 prime k e to the minus p of x over y1 squared. So that's that piece. This next piece, if I get a common denominator and all that good stuff, we're going to get plus, real quick, one of these y1s cancels. So we only got one of those on the bottom, which then when I multiply by that y1 squared gives me y1 double prime y2 over y1 cubed plus y1 prime y2 prime over y1 cubed. And then the other piece is going to be minus y1 prime squared times y2. And then that's going to be over y1 squared. So I'm pretty sure that's what we get when we plug in y2 double prime. I am not really confident at this point, but I think we got everything. All right, so there's our y1 prime. So then when we go to the, y2 prime. So then we need p of x times y2 prime. So that's going to give us plus p of x e to the minus p of x over y1 plus y1 prime y2 p of x over y1. So that was the y2 prime. And then we need to add q times y. So q times y2. So I'm going to go ahead and plug q times y2. And all of that needs to equal 0. So I'm really hoping that I haven't screwed up the algebra. But at this point, I am definitely not confident. All right, so good. I think I actually see something that I already missed. I'm pretty sure that in this piece there needed to be a k. And unfortunately, I've erased everything. But in that piece, that was the y2 prime Was it a ke to the minus px?
Yes.
Yeah? Okay, good.
Y2 prime ke to the negative big P x over
Okay.
y1. Yeah.
Okay, good. That way at least those two things cancel, which we kind of needed. So those guys cancel. So we already know that just from the algebra. All right. So now what? I mean, basically what we have to do is show that everything else cancels. So any thoughts? All right, so Trey just said get a common denominator. That's not a bad idea. I'm actually going to do something before that. So let's see, Brennan just said factor out a y1 and a y2. So kind of group things. So they've got all the things with a y2 or a y1. That's another good idea. I'm actually going to do one other thing first. I'm going to get rid of the ke to the minus px, because you notice how nothing else has that. So I want to get rid of that. And the way I'm going to do that is actually go back to the very, very beginning. We know that the ke to the minus px, that equals y1, y2 prime minus y1 prime, y2. So that thing that's I circled. So I'm going to do this in the same color blue down here. We have a minus y1 prime times y1, y2 prime minus y1 prime, y2. And I want you to notice what that becomes. This ends up being a minus y1, y1 prime, y2 prime over y1 squared plus y1 prime squared y2 over y1 squared. And I know that this probably doesn't look like much, but notice the y1 prime squared y2 over y1 squared, that cancels with this guy. Uh-oh, something's wrong with my algebra. Because that other piece was supposed to cancel with this one. Anybody see what I did wrong there? And this really sucks because I don't have my, like I've erased everything. Because the y1s cancel, which actually give me a y1 on the bottom instead of a y1 cubed. Did maybe when I built this, did I put a y1 on the bottom when it was supposed to be on the top? That's a legit question. All right, hey, while you guys check that, I gotta run real quick. I just got summoned by the wife. She knows not to interrupt me during class, so it's probably something important. I'll be right back. Okay, so did I make a mistake earlier? So my guess is yes, because again, some more stuff had to cancel out. So that we don't get derailed here with this, go back and look and see if I did some sort of an algebra issue somewhere. But basically what's going to happen as we continue, stuff's going to cancel out, and then we're going to be left with a y2 double prime plus y2 prime times p of x plus y2 times q of x. And all of that is going to end up equaling 0, which was what we were trying to show. And in fact, I know I did something wrong, because somewhere, like, we lost the y2 double prime. I could probably insert it again, making use of that original thing that we had. But there should be a y2 double prime somewhere. But this one, like, to get back to probably why Trey asks for it, is that this is an algebra thing. This really is a take this as your solution, plug it in, and everything should kind of fall out. So again, my guess is I botched the algebra somewhere, but I don't want to get us sucked into the algebra quagmire. At least, is this a good enough place to get you started, Trey?
Yeah, thanks.
Yeah, it ends up being an algebra thing. Okay, well, let's go look at number 14. And number 14, oh, I guess we didn't actually do the second part. But it says that if we have this as a solution, this y2, we know y2 can be written as u times y1, where u prime is given by what this formula that they tell us. And we're going to use that for number 14. So let me pull up my screen again so you guys can see it. All right, so we've got, first of all, look at what the second part of 9 says, 9 part B. It says that if you have a solution, y1, then you know that y2 is going to equal u times y1, where u is given by that k times e to the negative big P of x, so that's the antiderivative of little p, over y1 of x squared. And we're going to apply this, and we're going to apply it to the differential equation x squared y double prime minus xy prime plus y equals 0. And we're told y1 equals x. So I think I got all that information. Looks good to me. So I'm going to stop sharing and let's go back to the whiteboard. Okay, so first of all, notice that x is a solution to this differential equation. When you take its derivative, you get 1. Its second derivative is 0. So we're going to get 0 minus x times 1 plus x, which does equal 0. So I know that guy works. But since this is a second order, we know there has to be a second function to form its fundamental set. So let's see if we can find it. And we're going to use this trick where y2 is going to equal u times y1. We just have to figure out what y1 is. So we're going to start by getting u. So u is going to equal k e to the negative. Now we need to integrate negative x. Well, the integral of negative x is negative x squared over 2. So that was the big P. Oh, check that. What do I need to do first? I can't believe I fell for it. Yeah, and Brandon just said I got to divide by the x squared. So have you guys fallen for that? Ever? Like where you got the differential equation, but you forget to get it into the y double prime by itself form first?
Yeah.
Never, ever. Trey, you liar. Yeah, that one, I'm not going to lie, I fall for that every once in a while. It happens. Okay, so we got to divide by x squared first. So we get y double prime minus y prime over x plus 1 over x squared y equals 0. Okay, so little p is minus 1 over x. So if we integrate that, we get the minus natural log of x. So we have u equals k e to the negative natural log of x. And then we want to divide by y1 of x squared. So in this case, that's going to be x squared. Okay, so the negative is a positive natural log. E to that is x. So we get kx over x squared, which is k over x.
Bruce, I have a question.
Yeah, go for it.
The book for this problem, it says use the methods from number 9, but how it has it written is like y2 equals u of y1, and then I think they had the u prime equaling ke to the negative integral and then over y1 squared.
Well,
that confused me.
Okay, so in terms of, so you say it confused you because this was the u prime?
Yeah, and I guess like I didn't know how to integrate it.
Okay, so that just means that when we get to whatever this u prime is, then we integrate to figure out the u. But thank you for mentioning that because I was definitely going, we're going to go to a problem spot for sure. But if this is our u prime, if you kind of keep going, if u prime is equal to k over x, that means we sought to find u, but we integrate that, which in this case is going to be k times the natural log of x. And yes, technically it deserves a plus c, but we don't need to worry about that plus c because with integrating factors, right, in this case, we're just trying to find a representative. So then y2, we're going to take this and multiply by the original y1, which was just x. So we find that y2 is going to equal k times x natural log of x, where k was some arbitrary constant. So you can confirm that this works if you differentiate it and to get its second derivative and put it into the original differential equation. You should get 0. But this is clearly not linearly independent of x because they're not multiple of each other. So those two will form our fundamental set. So if we want to go and actually get the generic solution to this differential equation, so this is what any solution is going to look like. Y is going to equal c1x, because that was our first function that we knew was a solution, plus c2 times x natural log of x. And whatever that k is going to get lumped into our arbitrary constant. So the whole point of this one was that this is a way of actually finding your second function in your fundamental set. And sometimes it's easy to find one solution. Like, where did the y1 equals x come from? Well, obviously, they gave it to us. But that's one that you might be able to figure out just by looking at this original form and going, oh, I need some function that's decreasing in power. So let's try some sort of a polynomial. And that's like the easiest non-constant polynomial. So that might be a good first shot. And if you saw that, then you go, hey, cool, I got one solution. But knowing one solution is going to be enough. And we're going to see more of that today, where if you know one solution, that's often enough, because then you can build the rest of them. All right, so again, I apologize for the algebra issue with 9, wherever that happened, but assuming that we can get that algebra figured out and that number 9 is true, and it is. Are we good for 14? Kind of see the process? All right, I'm getting some thumbs up and nods. All right, awesome. Okay, so in terms of the homogeneous, okay, much better. Cool, I like that. In terms of the homogeneous, are we feeling pretty good about stuff from 5.2? I know no one asked me any questions from it, from that homework set, but in general, they feel all right. Let me just remind you the 3 different things that'll happen. So when we have that non-homogeneous with constant coefficient functions, so we're looking at a y double prime plus by prime plus cy equals 0. Remember what we do. We start by creating this polynomial. So it's just the coefficients a, b, and c. We make a quadratic. We find the roots. So find the solutions to this. And there were the 3 different cases. Case 1 is where you get 2 different roots. So I'm going to write here that R1 and R2 are different. And in that situation, it was super easy, because we saw that the e to the RT for those 2 different R's form our fundamental set. And so, boom, we're done. So that was case number 1. For case number 2 is where R repeats. And the problem with that was that we didn't have a second function. I mean, we knew that one of them was going to be e to the RT. And do you remember what the second one looked like? What's the second one look like when we have a repeated root?
P2, P to the RT, right?
Okay,
Or,
so yep, you just multiply by t. Good. So it's c2 times t e to the RT. So we did one of those integrating factor things, and we found out the integrating factor had to be linear, and boom, there you go. There's the second one. And then the third case was where the R were complex. So we have R equals A plus or minus BI. And do you remember what the form looked like there? What shows up when you have complex roots?
Euler's equation kind of stuff, the cosine of whatever times or plus or minus I sine of the function. I can't remember specifically right now.
Okay, but you're definitely on the right track, JP. So we use Euler's formula, and it leads to cosine and sine. And so what we get is an e to the at, so whatever the real part is, gives us an exponential. And then we get times c1 cosine of bt plus c2 sine of bt. So the from the Euler's formula, dealing with the power series basically with I. So talk about total monkey math. It's all about find solutions to that polynomial equation and then pick the right form. Okay, so that's where we got last time. So what we're going to do now is we're going to turn our attention to what if they are not homogeneous. So instead of this equaling 0, what if this is equal to, say, g of t? So what do we do now? So we're expanding our world a little bit, right? Remember how I was talking about we have all of the possible second degrees, and then we're going to restrict ourselves to linear, and then we're going to restrict ourselves to constant coefficients, and then we're going to restrict ourselves to homogeneous. So we're that little tiny chunk of that big world. Well, now we're going to open ourselves up to this chunk. So we're basically working our way out so we can do more. Okay, so the goal of today is, what do we do when we're in this situation? All right, well, here's the trick. Let me first start by giving you this theorem. So what we know is that any solution here, so this is going to be a theorem, that any solution can be written in the form y equals y sub p plus c1y1 plus c2y2. Now, the y1 and the y2, that's what you're used to. Okay, these two are our fundamental set. And I'm going to put here a set of solutions to the homogeneous. So those are the ones we already know how to find. So had this been equal to 0, and we create the polynomial and solve and then do that sort of thing depending on which case we get, the y1 and y2 that came from that are these. The yp, this is any solution to the non-homogeneous. So yp is any function that satisfies the differential equation we were given. So you already know that there are an infinite number of solutions. This is just saying all we need is one of them. If we know one of them, we can add it to the solutions from the homogeneous, and everything will work out. So first, let me show you why this is true, because I want to convince you that it does work. So think about this and differentiating it, and then getting a second derivative as well. Since we're adding three different things here, We know that we can differentiate each individually and then add. And so if you take a derivative and a second derivative, you're going to get the C1 Y1 prime, C1 Y1 double prime, same thing with the C2s. That stuff, when you factor it out, added together are going to equal 0. So they're going to go away. And what we're going to be left with is A times YP double prime plus B times YP prime plus C times Y prime, or YP. And if we know YP already is a solution, we know that actually is true. So this theorem definitely holds. I know I just walked through it verbally. If you actually want to see it, look in the book and they'll go through the algebra, but I don't think anybody cares about the algebra right now. I actually am really uncomfortable with the algebra after that first homework question that Trey asked. So I'm just going to go with it. Okay, so what does this mean to us? Well, if we want to find solutions, here's what we're going to do. We're going to start by solving the homogeneous. Because you'll notice that that's part of our solution. So we have to know the homogeneous solution anyway, so we're going to start there. And we like that because we know what to do. Okay, so then comes the second part, and this is the much more difficult part. And the second part is find any solution to the non-homogeneous. So we don't have to find a general or anything like that. We just need to find a solution. Any solution we can come up with, that's the one that we want to use. Because then we can add that solution to the non-homogeneous to the generic homogeneous linear combinations, and we've got our solution. So basically there's one more step. That's it. The extra step now is find something that works for the non-homogeneous. Solve the homogeneous like normal, and then find one more thing. So that's the process, and it doesn't matter what this thing looks like. We're going to do it that way. So let me show you an example. We'll start with something pretty easy. And when I say easy, it just means finding the solution or finding a solution to the non-homogeneous is quick. That's going to be the part that's hard, is figuring out what is y sub p. Because the other part we already know what to do. We make our polynomial, we factor, we find our solutions, and depending upon what those solutions look like, we get our different forms and blah, 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 blah. So let's try this. So let's start with y double prime plus 9y equals 9. So clearly it's a non-homogeneous, but it's still second order. It's still linear. It still has constant coefficients. So we're going to start by solving the homogeneous portion. So if this was equal to 0, we would create our polynomial that in this case is going to look like r squared plus 9. Notice that there's no y prime. So since there's no y prime term, there is no r in our polynomial. All right, so what are the solutions to this?
Isn't that positive 3i and negative 3i?
Good, Thea. those are plus or minus 3i. Move the 9 over, get a negative 9, take a square root. Whatever. So they are complex, which means y1 and y2 are going to be sine and cosine. So y1 is going to be cosine of 3t, and y2 is going to be sine of 3t. So that was step number 1. We solved the homogeneous. So now comes the hard part. Now we need to find any function, some function that will make this equation true. So does anybody see a y that will make that true?
E to the 3x.
E to the 3x?
Yeah. Oh wait.
I don't quite like e to
Oh,
the
sorry.
3x.
I was trying to solve the.
Yeah, and actually,
Yeah.
e to the 3x would have been perfect
Yeah.
if, you know, one of those
Yeah.
things was a minus or something like that.
Yeah.
What about y equals 1?
Okay, so Mikey just said, what about y equals 1? Do you like y equals 1?
Yeah.
What's the second derivative of y equals 1?
0.
0. So we get 0 plus 9 times 1 equals 9. I think we got ourselves a winner. So here is a solution to this differential equation. It's obviously not all of them. There are going to be many others, but there is one. And in this process, we need to find any solution to the non-homogeneous. Cool. Well, thanks for that, Mikey, because now we're good. Because what I know is that the solution to this differential equation, that every solution is going to look like 1 plus c1 cosine of 3t plus c2 sine of 3t. And if we go back to this y particular, that y particular is going to be when c1 and c2 are 0. Right? So that's one of the myriad solutions. But the other ones are all going to be this form with various c1s and c2s. So I think even this simple example, and I know I called it simple, this simple example still shows you that the hard part is finding the particular solution. The other part was easy. We already know what to do. Okay, so Monty just said, does y have to be constant? And can y equal x? So when you say y, do you mean the y particular? Yeah, okay. So because in terms of the general solution, no, there can definitely be things that are not constants. But could we try another constant? Well, no. It turns out that the only constant that's going to work is 1. Because if we change y to any other constant, its second derivative is still 0. And then 9 times that constant won't equal 9. But then what about y equal t? Would that work? Well, let's just see. If y is t, the second derivative is still 0. So we would get 0 plus 9t. Well, does that equal 9? No, they're not identical. So unfortunately, that wouldn't work. So in this case, y equals t would not be a solution to either the homogeneous or the non-homogeneous. Okay, good. You're seeing what's going on. All right. So I guess we're resigned to it's trying to find that YP. So let me show you some other examples that lead to kind of specific types of potential Y sub P's. And this is definitely going to play upon our pattern recognition thing, right? Like I talk about this a lot. I'm firmly convinced that differential equations is all about pattern recognition. And this is another case where you're going, all right, I know I've got my constant coefficient, so I'm going to find my solutions to my homogeneous and get my fundamental set, blah, blah, blah. But then I got to find my YP. But how I find my YP is going to be determined by what my differential equation looks like. So here's another one. Let's say we're looking at y double prime plus y prime minus 2y. And this is going to equal 4t squared minus 2t plus 1. So a little more complicated, but not terrible. You compare this to the example we just did. Well, instead of having a constant, we've got a polynomial. But other than that, it's the same. All right, so let's start by solving the homogeneous. So the homogeneous says make this polynomial, which is going to be r squared plus r minus 2. We're going to set that equal to 0. So this factors r plus 2 times r minus 1. So that tells us that y1 is going to be e to the minus 2t, and y2 is going to be e to the positive 1t. So we always get e to the rt, whatever the solutions for r are. All right, so good for that part? All right. So now we got to try to find a particular solution to this specific differential equation. So we need a function that when we put it in here gives us 4t squared minus 2t plus 1. All right, so what kind of function do you want to try to find? What do you think the particular solution is going to look like?
A polynomial of some sort, I'd have to guess.
Okay, so what do you guys think of Thea's guess? Is she on the right track? All right, well, at least you got support from Brennan, so, take that.
That's what matters,
As long as Brennan's on your side, you're good. Okay,
Support
so
from high places.
yeah, so I think a polynomial is a great guess because you take a derivative of a polynomial, you get another polynomial. The second derivative is also polynomial. So we're going to be combining all kinds of polynomials to get a polynomial. So I think that's a great approach, is let's try a polynomial. How big? What degree?
Second,
Okay.
because
So,
the max degree on the right side is second. So
all right. So again, Thea's running with the ball for us. And so she already said polys, I think is good. And now says, well, how about a second? I think second degree is perfect because we know that when we differentiate, the degree goes down. So the biggest thing we might need is a t squared. And the only place that that can show up is in y. If we went with y being something bigger, t cubed, t to the 4th, t to the 5th, that stuff's going to stick around and we don't have it anymore. And as we differentiate, well, we're not introducing anything of a bigger degree. So I think that's good. So basically, this is what I think. I think the y particular is going to be some sort of second degree polynomial. And it's going to be an AT squared plus BT plus C. So really the question is, can we figure out what A, B, and C are? Well, that's going to be doable. I was going to say easy enough. I don't want to use easy. But that's going to
Isn't
be
that a
doable.
negative 2t? Oh, sorry, that's b.
We good? I'm just
Yeah,
going with the
yeah,
generic.
I spaced out.
That's all good. Okay, well, let's just see what the different derivatives are and see what that forces A, B, and C to have to be. So the derivative of this is going to be 2AT plus B. And the second derivative then is 2A. So if I put those back into the original differential equation, that gives me 2A plus 2AT plus B minus 2 times AT squared plus BT plus C. And that needs to equal 4T squared minus 2T plus 1. So really this just comes down to what does this force A, B, and C to equal? So what I'm going to do is I'm going to group everything on this left-hand side by the coefficients on the powers of t. So on our t squared, there's only one of them. It's going to be minus 2a times t squared. The t's, I'm going to get 2a minus 2b. That was this 2at and the minus 2 times the bt. And then in terms of constants, I'm going to get 2a plus b minus 2c. And now I'll just equate those and create a system of equations. So I know that minus 2a has to equal 4. I know that 2a minus 2b is going to have to equal minus 2. And then 2a plus b minus 2c is going to have to equal 1. And now it's just a matter of solving that system. So this gives us a equals negative 2. If I put that into the second one, I get b is equal to negative 3. Nope, I totally lied. I think that's b equals negative 1, actually. Yep, I like that better. And then when I plug those in over here, I'm going to get c is equal to minus 3.
Minus 2.
I put it in a matrix and solved it if you want me to give you the read off.
Is it minus 2, minus 1, minus 3?
Yep.
Okay. Then I'm good. Okay. So what that just told us is that a particular solution, remember this is just one of the very many solutions to the original differential equation, is minus 2t squared minus t minus 3. But now that I've got that particular solution, I'm ready to write my solution, the overall solution for this differential equation. It's going to be minus 2t squared minus t minus 3 plus c1 e to the minus 2t plus c2 e to the t. But it has that same form that we knew we had to head for, which was a particular solution, plus the linear combination of our fundamental set to the to the homogeneous differential equation. So again, the hard part for sure was finding YP. The other two are easy. I mean, they're so easy that it gets to the point where you're like, why do we even bother doing this anymore? I'm solving a quadratic. Whoop-de-doo. Obviously, the reason we do it is because it's necessary. But it's the other part that's going to take our work. All right, so think about this. If you got a polynomial, that's what your function, your derivatives are equal to. If that's what your f is, a polynomial, start with a generic polynomial as your guess for your particular. And then you can use the differential equation to determine what the coefficients need to be. All right, so how'd that one go? Questions on that one? Is anybody bored yet? I have a really hard time fighting my boredom with differential equations. Just because it's the same thing over and over and over and over, right? You're new to it, so you haven't experienced that yet. But I promise you, by the end of the quarter, you're going to look at things like this and go, oh my God, I have to solve a second order. So boring. All right, well, let's do this. Let's change this function f, because now you see what to do with a polynomial. I could give you any polynomial and you have an idea of what to do. But what if we change it a little bit? So let's go with this differential equation. Let's go y prime minus, or sorry, y double prime minus 2y prime plus y is equal to 3e to the 2t. So this is another non-homogeneous. But let's see if we can figure out what the solution is. So we're going to start with the solution to the homogeneous, which means create our polynomial and solve. So the polynomial we need to solve here is r squared minus 2r plus 1 equals 0. That factors to r minus 1 times r minus 1. So we're in that situation of a repeated root. So what are our fundamental set going to be? What two functions form the fundamental set?
E to the, or C1 e to the t plus C2 t e to the t.
Okay, good. Thanks, JP. So the first one's going to be e to the t, so e to the 1t. And since I can't use e to the t again, I have to slap a t on it. So there are our fundamental set. Beauty. Okay, now the fun part. And you can feel the sarcasm in my voice. Let's find a particular solution. All right. Well, let's do like what we did last time, which is we may not be able to look at this and say exactly a particular solution, but I bet you could give me a form for the particular solution. What kind of function do I need so that if I plug it into this, gives me 3e to the 2t?
Definitely e to the 2t times some sort of constant.
All right. Did you hear how sure Thea was? I love it. Definitely e to the 2t. Yeah, no, it is. It's definitely going to be an e to the 2t because when we differentiate e to the 2t, we're going to get multiples of e to the 2t. And so the question really is just how many of them. All right, so I'm with you, Thea. I agree. Let's go with e to the 2t of some type. So we'll multiply it by some unknown. But let's see what we get when we plug it into the differential equation. So then the derivative of this is 2a e to the 2t. And the second derivative is 4a e to the 2t. So if we put that back into the differential equation, we're going to get 4a e to the 2t minus 4a e to the 2t plus a e to the 2t. And what we need is for that to equal 3 e to the 2t. So these
So
are
then
all,
A is just equal to 3, correct?
yeah, so you just
Yeah.
combine those, they're all the same. So you get 4 minus 4 plus 1 is 1, a e to the 2t, which just like JP just said right there, it tells us that a is equal to 3. All right, so here's our solution then. We need the particular solution, and we just saw that 3 e to the 2t is a solution of this differential equation. And then we add to that the linear combinations of our fundamental set. So we'll add to that c1 e to the t and c2 t e to the 2t. But there you go. There are all of the solutions to this differential equation. Anything that solves that original thing looks like this with various C1s and C2s. Now, this one probably didn't seem as bad because the algebra, I think, was a little bit easier. But again, the bulk of our work was in order to find that y sub p, that particular solution. And that's pretty much standard. All right, let's do one more, and then we'll call it a day. But same old story. We're going to start with this differential equation. We're going to try to figure out the solution to the homogeneous part. And then once we've got the solution to the homogeneous part, we're going to see what kind of form our particular solution should take and see if we can find one that actually works. All right, so we got y double prime plus 4y prime equals sine of t. So like always, let's start with creating a polynomial for our homogeneous. So this one's going to be r squared plus 4r equals 0. There is no constant piece because we don't have any y's. So factoring this, of course, gives us r times r plus 4. So what are our fundamental set? What are y1 and y2?
E to the negative 4t and
Okay.
t times e to the negative 4t.
So one of them for sure is e to the minus 4t because of this. But the second one isn't t e to the minus 4t.
It's one, isn't it?
It's
Wouldn't it
just
just be
one.
y? Wouldn't it just be y equals e to the 0, which is 1?
Yeah,
Yeah.
so it's going to be
Yeah.
y equals e to the 0t, which is just 1. So it's not a repeated root. There are 2 roots, which means we get e to both of those powers times t. And whenever you get a 0, you know that that's just going to give you a constant. And you can see that, right? If y is 1, its derivative is 0, its second derivative is 0, And so that will be a solution to that homogeneous part. All right, cool. So now the part. What about the particular solution? So anyone want to give me a guess for a form for this one? Like what kind of function do we need so that when we plug it into this, we end up with a sign?
A cosine function, or a cosine or a sine function?
So what are you guys saying? JP just threw out
One of
cosine
the two.
or sine. Those seems pretty much reasonable, right? Because the derivatives of cosine and sine are, of course, sines and cosines. So it's definitely possible that those things, when we differentiate, will leave us with a sign. Okay, so what do you want to use, sine or cosine? Which one do you want to try?
Go with your
so
favorite cosine.
Let's just put cosine, and yeah, that's bonus points right there. Today, but today only, I'm not going to make fun of Wes because he just gave me a good answer. So let's try cosine. Okay, so if a is or if y is a cosine of t, then y prime is minus a sine of t. Cool, we got some signs. Y double prime is going to be a minus a cosine of t. So let's see what happens when we put that in. We get minus a times the cosine of t minus 4a sine of t. And let's just think about what's going to have to happen for this to equal sine. Let's start with this first part. We got to get rid of that cosine, right? So what does that force a to equal? It's not a trick question.
0.
It's got to be 0 to get rid of that.
But
what's
that
the
would
problem
also
with
get
a
rid of your
equaling 0?
sign.
Yeah, it also gets rid of sine. It's
So
basically
no
saying
good.
our particular solution is 0, which is a bogus bullshit answer. Okay, so this is when we go, stupid Wes. Told us to start with cosine. It didn't work.
Is it a sum of cosine and sine?
Well, what if we had just tried sine? So let's just say instead it had been b sine. If we had differentiated, we'd have gotten b cosine, which then gives us a minus b sine. And if we had set that up by plugging in a differential, we would have gotten minus b sine plus 4 cosine, or sorry, 4b cosine. And you notice that the same issue happens. To get rid of the cosines, that would force b to equal 0, which then means the sines got rid of, and that's a problem. So just cosine or just sine is not enough. So I wasn't ignoring you, Thea.
Yeah.
I mean, I was, but it wasn't, I mean, it was intentional. I'm ignoring because you were kind of spoiling it for me. What we need to do is actually make it a combination of those. Because now, put our plus in here. This makes it so that we've got a chance. There are going to be potentially values of a and b that will give us what we want. So now what we're going to have is a system. If we look at, say, the cosines, I've got minus a plus 4b. That came from the cosines. And what I know in the end is I need 0 cosines. So those are going to have to add up to 0. And then if I do the same thing but look at the signs, I'm going to get minus 4a minus b. That's those. And what's that going to have to equal?
1.
1, because I've got one sign at the end. So now I've got a system of equations. I know what to do. I can go ahead and solve this. And when I solve this, I'm really nervous because I just did this in my head. But I think it gives me a equals minus 4/15, which then makes b equal minus 1/15. Nope, that is definitely not right.
No, it's
Minus 4/15, 4/15.
no, it's negative 4/17 minus 1/17. Apparently from Symbolab.
Okay. I buy that. I was off. I was going off 1 from 16. I just went the wrong way. So 4/17 minus 4/17. That works for the first one. Plus 16 plus 1. Yep. Okay. Symbolab's right. And as always, I definitely welcome our robot overloads. I don't mind. I really don't. Let Skynet happen. I welcome it with open arms. All right, so there's our A and our B, but now that means we've got our particular. So we can put that all together, and here's our solution. Our solution is going to be y equals minus 4/17 cosine minus 1/17 sine. Let's put the A's and B's in there. So there's our particular solution plus C1 e to the minus 4t plus C2 times 1. Okay. So hopefully you're seeing that in general, the process is pretty clear. You solve it as if it's homogeneous, you get your fundamental set, but then you got to find your particular. And that's the challenge, right? I mean, honestly, that was the hardest part, was figuring out what is this thing that does actually work for the differential equation. But I've shown you 3 different kinds. I showed you a polynomial. Make your guess of a polynomial. Showed you one where it was exponential. Make a guess of the exponential. Showed you one where it was trig. Make a guess of the trig. And that's really what we're going to do. We're going to look at this side, and this side is going to tell us what to do. Obviously, what we'd rather have is some sort of a systematic approach so that we don't have to just look at that and guess a form. And that's what we're going to do over the next couple of days. Is we're going to look at, okay, is there a systematic way of doing this? And the answer to that is a yeah, kind of. There's a very systematic way of doing it. Sometimes it's faster not to do that systematic way. But I'll introduce you to both, and we'll talk a lot about how what's on this side tells you what to go for, what to look for. And often it leads to a system. And you can use that system of equation to find those values. All right. So I think I'm good for what we did today. We're also out of time. Man, this is the first time we used the full time in a long time. So I'm going to pause the recording.